If you're to take any object and place it underneath a microscope, what you'll notice is that there's all sorts of irregularities in the surface. We never have a perfectly polished, smooth object down to the atomic level, and because of that, we end up with surfaces that look a bit more like this in the real world. Now, on the left, we have dielectric. This is a dielectric example, and on the right, I have a metallic example. So, on the dielectric side, we end up with something like this. And what you'll notice is that not much really changes. With dielectrics, most of the light is bouncing off in a diffuse way, and adding all these irregularities will not really cause much of a visible difference, because light rays are going in all directions anyway. However, on the metallic side, we have a very different story. Take a look at this. Light rays now are going in all directions as if it was behaving in a diffuse way. But it's not actually diffuse behavior necessarily. It's still bouncing off in a specular way. It's just that all these different peaks and valleys now cause those reflections to reflect at different angles. Now, another thing to keep in mind here is that this applies to the direct reflections. We actually have a different thing happen with Fresnel, and I'll talk about that here in a second. But with the direct specular reflections, what we could say is that major changes will occur, and now it's possible to see the light source from different angles. What that means is that when you go to change the roughness parameter, what you're mainly looking at are the direct specular lobes, those direct highlights. And the more you make something rough, the more blurry those highlights are going to get. Now check this out. When it comes to Fresnel reflections, we see something a bit different. No matter how rough you make a material, once you approach the grazing angle, the roughness is going to decrease. And if we look at a surface from a perfectly flat vantage point, then our reflection will behave in a purely mirror-like fashion. And the reason why that happens is because if, let's say, light rays are just kind of skimming off the atoms at the very edge right here, those are the atoms that reach your eye. If the light rays go into one of the valleys and they bounce around, those light rays never actually reach your eye. And so if we take a look at this plane right around here, you'll notice that, well, we're still basically looking at the reflections of something as if it was a flat surface. And because of that, it acts as if the roughness on that microsurface is at a value of 0. But for right now, I just want to point out that the Fresnel roughness and the direct specular roughness do behave a bit differently. So now that we've talked about roughness, let's talk about absorption. As I've mentioned before, when light hits an object, it has the option of reflecting, of transmitting through the medium, or being absorbed. Now, I'm not going to get into the scientific details of what absorption actually is, because that's not really as practical to what we need as artists. But let's just talk about the general idea and then how that relates to parameters that we have within the albedo/base color of the principled shader. So white light is made up of red, green, and blue. Think of that as adding together. And by now, if you're not familiar with some of the basics of light in general, we could think of light as photons, which are tiny little particles that hold energy. And we can also think of them as waves. And these waves represent different colors. Red has a lower frequency, a bit more like that, whereas blue has a higher frequency, like this. So if you add all these different, let's say, frequencies of light together, you end up with pure white. Now, how is it that we see color? Well, like I said, it's through absorption. So what ends up happening here is that if something is green, the red and the blue colors are being absorbed, and what's left over is green. If we take a specular reflection like this, we could say that the specular color remains mostly white. However, it is very possible here that some of that purely white color has been tinted in a green direction. And so even though we usually just assume that the specular color is white in most circumstances, it oftentimes actually gets tinted a little bit by the color of the object. But for the most part, for most dielectrics, most materials, you can consider this as white, or whatever color the light is when it bounces off. However, look at what happens when we have diffuse reflections. It goes inside the medium, the atoms bounce around, or I should say that the light goes from atom to atom, and every single time the light is casted to the next atom, a bit of the energy is absorbed as heat. So this red and this blue, it gets absorbed with every single bounce, and then by the time it leaves the object, the ray is now at this green color. Now, as we perceive color on an object, we're actually perceiving the general color that things end up becoming. And so, as you can imagine, the more bounces you have, the darker this color gets because more and more of the red and blue is being absorbed by the atoms. But as we look at objects, we just see a general color. That's what we're talking about with this albedo/base color. And also understanding the way in which light bounces around these different atoms and changes its color along the way will impact subsurface scattering once we get to that section. It's essentially the same process, except instead of going a little bit into the surface of an object like diffuse reflection does, we're going much, much further, and this effect becomes noticeable as light travels through the medium. It might be why, for instance, blue gets a darker shade of blue the further down you go into a body of water. But anyway, we'll get more into that once we get to subsurface scattering. For now, just know that that is in general how this absorption works. So let me tell you why this is important. We have 100% of the light energy, and we know that some of that energy is going to be reflected in a specular way, some of it will happen in a diffuse way, and some of that energy will be absorbed as heat. Well, this heat component, this absorption, is usually pretty significant. About 30% of the energy, it depends on the material, but usually around 30% is turned into heat or is absorbed. 4% ends up seeing about a specular reflection for a dielectric, and that only leaves 66% of the reflection acting in a diffuse way. So now that we know about 30% of the light is being absorbed as heat, that's going to make a very big impact on how we handle the base color and the albedo multiplier. Because here's the deal. If we ever set this to a value of 1, like it is right now, we just have 1, 1, 1, this color is very unnatural. It's not something that you would actually ever see in the real world. Why is that? Well, that's because light will be absorbed as heat in the real world, and it won't ever give you a diffuse reflection at full blast right here. Instead, what you ought to do is this. Go to the base color, and your new white lives at 0.7. That's going to account for, again, the way that light is absorbed by the object. And what that will do in practice is it'll improve the quality that the light has when it hits these objects. You're less likely to see harsh, overexposed highlights. You're less likely to see these unnatural looking saturated colors because you've now brought it down to a value of about 0.7. Also, for practical purposes, if you ever have a scene and you want to really emphasize a specific color, by setting your colors to 0.7 like this, it gives you a bit of extra room to emphasize things if you want to. So if I want to exaggerate something that's red in my scene, Now that everything else is around 0.7, I have that extra room to do so. And so what that all means is that because of absorption, 0.7 is good. You can do that right here, or you can go to the albedo multiplier and just say 0.7, and then you can just pick whatever colors you want. So you just pick colors as you usually do, and you leave this multiplier at 0.7. Okay, so now that we know a good bit about diffuse reflection, specular reflection, roughness, and absorption, now we're ready to take a look at reference, go through a few exercises, and recreate some basic materials based on all the theory that we just learned about. So we'll do that in the next lesson.